So I titled this simulation, presentation, or this lecture as Modeling and Simulation of Turbulent Flows, because you'll see that those are going to go hand in hand. You'll find that it's, except for some basic experimental correlations, there's no way to find analytical solutions for turbulent flows without the use of computers and computing. They come in really handy and very powerful in assisting us computing turbulence. And so today's lecture and slides will be on turbulence, and so we will do the same on Wednesday as well. And I'm quoting an airline passenger who says that turbulence makes them sick, and I heard one airline passenger once say that. So I like quoting that. Turbulence. That's a kind of definition, a little definition of turbulence. But what do you understand? What do you understand when we say turbulence? Kind of want to get an idea of because you've used the word turbulence. Everyone uses the word turbulence. They butcher the meaning of turbulence. Once the public gets hold of a word, they use it inaccurately. So what is your understanding of turbulence? So whatever, the high level meaning, yes, Mason.
Okay, so probably the butcher.
Sure, yeah.
Just like random motion in a fluid.
Okay, random motion of.
Lots of vortices, stuff like that.
Okay, but what do we mean by random?
It's not. Gosh, I don't know. I shouldn't
Okay.
have raised my hand.
Okay.
That's the thing.
No, that's fine. I mean, because that's a correct answer. It is a correct answer, but we often also misrepresent the word random and the word chaos, okay, which is another thing that is associated with turbulence. Any other takers? Turbulence, no. Yeah.
So the fluid might have a very high Reynolds number with a lot of vortex.
Okay, so I see a pattern here emerge that these flows have a lot of vortices, a lot of rotation. But vortices are not associated with turbulence. Okay, so we saw irrotational flows that have a big vortex in them. So although vortices are an essential feature of turbulence, okay, they're not turbulence. Whenever you see vortices, doesn't necessarily mean there's turbulence. Okay, any other? Yeah.
In heat exchanger design, the one thing I remember of turbulence that you need good turbulence so we can
mix well. Very good. That's a feature of turbulence, that turbulence mixes things very well. So remember the turbulent boundary layer. We had this kind of very, very sharp, very large gradient near the wall, and then the boundary layer, it just kind of picks up nearly the uniform flow. That's because there's a lot of mixing of momentum in that boundary layer. So that's correct. Okay. So why do we want to study turbulence? Before we talk about what turbulence is, most flows in engineering are turbulent. It's kind of a basic assumption before you even start looking at a flow. It's probably going to be turbulent. Of course, the right way to do it is to look at the Reynolds number, see a characteristic Reynolds number for the problem you're looking at, and you may, if you're on a flat plate or you're doing like flow over a flat terrain, you're probably going to hit a distance at which the flow is going to transition, and the flow is going to become turbulent. If you're looking at pipe flow, so typically think about 10 to the 5, 10 to the 6. That's a rough number for the Reynolds number where we say the flow has become turbulent. And interestingly enough, at high Reynolds number, then inertia is much larger. The inertial forces are much larger than viscous forces. And we'll see a little bit later how actually it's the inertial terms that create all sorts of complexity for us in addressing turbulent flows. Turbulent flows, we're starting to get a little bit more mathematical here. Turbulent flows are characterized by a fluctuating velocity field, a velocity field that changes value in time. So if you put a measuring device, you're measuring velocity at one point in space, that velocity is going to fluctuate, it's going to oscillate over time. And also, if you move your probe in space, you're going to be measuring different things. Like take the pipe flow at high Reynolds number, put a probe at the center line, move it downstream, You're not going to measure the same center line velocity. It's going to change in space and also in time. It's going to oscillate. We say that the velocity field is random. We'll have a better understanding of that word in a second. Turbulence highly enhances the rates of mixing of momentum, heat, etc. So sometimes it is desirable. We want to have a turbulent flow because we want to mix things very well and quickly, and that's why when you put sugar in your cup, you just kind of stir it to promote mixing. Okay, make it a little bit turbulent. Okay, these are a couple of simulations that I like to show every time I give this lecture. And you may think of turbulence as air going really fast, but that's the case only for air. You can have turbulence at low speeds. What characterizes turbulence is really an infinite number of scales. There are scales in the motion that are of the size. So I want you to focus here. When I say a scale, think of the size of a vortex over here. Okay, now you see the entire flow, there's this giant vortex over here that's moving, that's nearly the size of the entire domain. Pay attention, look at the large scales over here. Okay, there's like these scales that are moving, the whole thing is moving. Okay, you don't see it, but if you look further enough, the whole thing is moving, but also as there are little pieces that are moving, that get smaller and smaller and smaller and smaller and smaller. Does this make sense? Yeah, you see the whole domain is moving, and then each one of those is moving in bulk, and then each tip of those is moving, and so on and so forth. So there's a very large number of scales going from the size of the flow, the domain itself, the domain of interest, all the way to very, very, very small scales. And we'll realize later that these very, very small scales are actually the molecular scales. Those are the scales that will dissipate energy. Again, try to focus on this animation. You'll see that there's motion with the bulk of the flow. The whole thing is rotating, but there's also smaller and smaller motions. Okay, that's what you see when you're driving, to across the industrial regions of Utah. You'll see these smokes, these chimneys, these smokestacks. They're emitting this steam, and you look at the steam, you see it's really turbulent. Okay. Another one, looking at the mixing of two different tracers in a fluid, and it's just really mesmerizing. Again, you have structures. You see the whole thing is spinning. This whole thing is spinning. This is a large structure. Okay. And all the way down to small structures. Okay, so this is still eye candy. This is still eye candy. I mean, in the end, we need something mathematical, something tangible with which we can tackle. This is just descriptive. So we're just trying to get a feel of turbulence, okay? Another characteristic of turbulence is that it is random and chaotic. We hear those words said all the time. But one thing to think about when you think about chaos is that you cannot repeat the same turbulence experiment and get the same instantaneous results. Okay? And the reason is not that the flow is not deterministic. I mean, in the end, the Navier-Stokes equations, whatever we derived so far, they are valid for turbulent flows. Okay? And those equations are deterministic. The problem, however, is that the experiment does not have the same exact initial and boundary conditions. Okay, we'll get to that in a second. Okay, characteristics of turbulence: mixing, vorticity, tremendous length and time scales. And historically, when Reynolds started looking at pipe flow experiments, this is a pipe with a tracer in the middle. Okay, and as you increase the flow rate and therefore increase the Reynolds number, you start seeing these little wiggles form. So we're still at transition, what we call transition. And we're fully transitional over here. And then suddenly, you've transitioned to turbulence. Okay? We're turbulent. Velocity is fluctuating in time and in space. It's changing. Okay? You're fully turbulent. However, the flow is still kind of, on average, is still the same, right? It's still moving that direction. You need to have your average velocity because of mass conservation. Your average velocity at any cross-section of the pipe needs to be equal to the average velocity at the inlet. So we retain those properties, right? Those average properties, and that's going to be a key element in our tackling the turbulence problem. Okay. So if you were to put a probe, spike flow rate coming in, you put a probe over here. In laminar flow, you would measure same velocity all the time. Okay. If you plot the velocity as a function of time, you will measure the same velocity. If you're transitional, every now and then you'll measure a couple of wiggles. If you're turbulent, this is what you'll measure. Completely chaotic, completely, you'd say unpredictable. You'd run the same experiment, you're going to get a different profile. Yes?
So over time, would you say the turbulent average is still the same as the laminar average?
Yeah, has to be. But it depends on what you mean by that average, okay? So you have to define your average very well. Is it over a long period of time, you know? And if in this case, it's easy to define that, but what if you have a time varying average? So what if you're changing the inlet flow rate? And what if the laminar case goes up and down, right? So you have to know how to define that average over a period that you can still retain that property. But there's another average called the ensemble average, which we will discuss in a second or in a few minutes. There's a lot of things we're going to discuss in a second, okay? All right. So what is going on? Why do we see this? Any ideas? Yes?
You had mentioned before that when the Reynolds number is really high, if there's any kind of perturbation, then it'll, I don't know if magnify is the right word, but it'll propagate.
Spot on. That's the right answer. Yes. So what Mason is saying is that a key feature here in that we observed in this experiment, at least with the pipe flow, is that as we increase the Reynolds number, it seems that in practice, you know, any slight perturbation to the flow, whether be it coming from, you know, someone opening the door, hey, do you want lunch, for example, they perturb, you know, the ground a little bit, or like a little earthquake happens, or you bump into the table of the experiment, produces a perturbation at a certain Reynolds number, that perturbation is going to grow. It's not going to dissipate, okay? So it seems that the flow is sensitive to a single parameter known as the Reynolds number. We know the Reynolds number, so it's known as the Reynolds number. It's not the velocity, not the viscosity, not the pipe diameter that is affecting this. It is the Reynolds number, okay? And this behavior is similar to what is called chaos in dynamical systems. So if you have the chance to take a course in dynamical systems, I recommend you do that. Or if you want to do some cool reading, take a course in dynamical systems. There are also a couple of books. One book is called Chaos that talks about the theory of chaos. I mean, it's just beautiful stuff. But there's a historical perspective to this, and I want to relate turbulence or dynamical systems to the Lorenz. Are you familiar with the Lorenz equations? Yeah, okay. I want to relate this to the Lorenz equations. So Lorenz was one of the first guys who discovered this phenomenon, the phenomenon of chaos. There was another guy called Yoshida who in Japan who also discovered this, but you know, Lorenz got the claim to fame, but Yoshida historically caught on to that a little bit earlier. Anyway, so what happened with Lorenz? He was modeling some atmospheric flow. So people from in atmospheric science kind of caught on to these beautiful fluid dynamic phenomena early on before engineers did. And Lorenz was running some computations. Okay, he developed a reduced model for flow in the atmosphere. I don't know the details, but you can read up his paper. It's pretty simple. He came up with a system of ODEs. Let me show you the ODEs. So he came up with these three ODEs: dx by dt equal some parameter times y minus x, and dy by dt some rho x minus y minus xz. X, y, and z are not position. They're properties. Think of them as velocity components, okay? X is the u velocity component, y is the v velocity component, and z is the w velocity component. But he reduced the system, he kind of got rid of all spatial change, so reduced it to a set of ODEs that are only a function of time. And these have three dimensionless numbers, sigma, rho, and beta, okay? And what he did, he ran the simulations, and at the time, in the 40s, you know, it was very expensive to run calculations on a computer. They had these kind of cathode tubes and punch cards and whatever. So he ran a simulation, and then he is like, okay, I need to get home, go get me some lunch, get some sleep, and then come back later. So he stopped the calculation and truncated the results to 8 significant digits, okay? And then he came in the next day, and he came in the next day, and apparently he had run another simulation a longer simulation without truncating the numbers. He was just repeating a simulation, okay? And he had a set of results with the full simulation, let's say up to 60 seconds of the motion. And then when he truncated at 20 seconds, let's say, and then came in the next day and put in the numbers and ran, and he did his thing, drank his tea, etc. And then once the results were ready at 60 seconds, he looked at both results, was like, this doesn't make sense. They didn't match at all. They did not match at all. And that's what he called chaos. And it turned out that truncation, that very, very small truncation from 10 significant digits to 8 significant digits, caused so much change in this system of equations, and he dubbed that chaos. And so in other words, really what chaos is our inability to know everything we can know about a system, because there's always going to be a slight factor in perturbation, or in the boundary conditions, in the initial conditions, or in your restarting a calculation that will put you on a different path for the solution, okay? So we're going to simulate this system now. It's really easy. You can put this in your MATLAB in ODE 45 and then solve the system of equations. So here's what we're going to do right now. We're going to fix we will fix two parameters, sigma and beta, and we're going to change rho. Rho is the equivalent to the Reynolds number in fluid flow, okay? And we're going to test this with two different initial conditions. The first initial condition is 0.1, 0.1, 0.1 for x, y, and z. So it's an ODE system, right? You need initial conditions to solve it. It's ODE function of time. And the second set of initial conditions, it's the first one plus 10 to the minus 6. Just add a very, very small number, right? You think that, oh, come on, this is in the noise. It's not going to matter, okay? So let's see what happens. We're going to vary rho. For rho equal 5, I'm plotting here the solution of x versus time. It's an ODE, right? So think of this as the u velocity. And that's kind of the solution. Initially, there's something going on, and then it stabilizes over time at a value, let's say 5, maybe over here. And this is for the first set of initial condition, second set of initial conditions, and this is the difference between both solutions. Okay? It's nearly 0. The error is in the noise, 10 to the minus 15. Okay? We increase rho a little bit. They make the Reynolds number, an order of magnitude higher. Rho equal 20. You get something different for x, right? Something different here for the other set of initial conditions. Yet, the difference, that little perturbation we did in the initial conditions, is insignificant. Okay? Again, we go for higher Reynolds numbers, and you get interesting behavior for the x value, first set of initial conditions, second set, but the difference is still 0. Look at that value, 24.2. Now I'm going to go to 24.3. Look what happens. That little perturbation to the initial condition, beyond the threshold value of rho, fixing beta and sigma, we see a serious difference between, look at this is significant compared to the values, about the order of the velocity, that error over there. The difference between the two solutions. So here's what I'm going to show you here. This is an animation of the solution as we change rho. So again, I'm plotting x versus time for the first set of initial conditions, second set of the initial conditions, and the difference between both solutions. And I'm going to change rho. Okay? So it's going to animate. You can focus on this one if you want. No change, no change, 10, 12. Remember 24.3 was the number? Look at that. Look at that. Although over there, they kind of look the same, right? But you see a significant difference over here with this very small change in the initial conditions. And that's chaos. That's what we call chaos. It's really not something that mysterious. It just says these systems are so nonlinear that any slight change in a boundary condition, okay, or initial condition, could put you in a completely different trajectory. Which makes me think about, climate models. When you hear climate models and the misinterpretation from the public about what's happening with climate change. I'm not a climate expert, but we can't predict the weather for 2 days. Yet we have these models that people claiming, in 100 years this is what's going to happen. No, you have no idea what's going to happen. You present those data with uncertainty. That's all we know. We present a best case and a worst case scenario. And the worst case scenario, what's the probability of that? Is it 1%? It's happening? But unfortunately, the public doesn't understand this. That we have a lot of uncertainty in these models, okay? And climate, it's got like 6,000 parameters that you want to tune, and we know none of which with certainty. And you can see a slight uncertainty in the initial condition could land you in a different solution. Could be the difference between an ice age or turning into Venus. No, seriously, I mean, when I hear people get so scared about this, I'm like, no, let's focus on engineering solutions that we can handle. We'll deal with it, and as these changes hit us, I'm not saying we don't reduce our carbon emissions, we don't reduce things. I mean, those are healthy things to do, but let's have a rational discussion about this. Okay, that's my rant on climate change because, anyway, okay, I'm not a climate change expert, so I have no idea. But I saw a talk a couple of years ago by one of our climate scientists. He was there's the temperatures could drop by -6 and could increase by 4 degrees. But we're going to take the increase in 4 degrees because that's going to be the worst case scenario, and we're going to go with that. I'm like, what? Anyway. So, but you see, this is a silly dynamical system. It's nothing. It's a set of ODEs. Imagine adding so much complexity. Anyway, so but it's all fluid flows. Okay, such a complex dynamical system of equations that is chaotic, and that's what we mean by chaos. Is beyond a certain threshold of the Reynolds number, any slight perturbation in the flow is going to cause you to land on a different solution. Okay? And in practice, that's inevitable. There's no way we can know. You run an experiment, You're running the drone experiments now, Hayden. Imagine you go and repeat the experiment. I cannot expect to ask you cannot expect me to ask you, hey, I want the instantaneous results. No. Rather, we should talk in terms of statistical averages, okay? And that's going to be a key important feature in us describing turbulence. Anyway, so the previous plots show that for a critical value of the coefficients, etc., the system becomes highly sensitive to small perturbations, and this coefficient is the equivalent of the Reynolds number. I think it is actually the Reynolds number when Lorenz reduced the equations. I don't know the full derivation, but I think this row is actually the Reynolds number. Okay. It's not that turbulent flows are totally unpredictable. In the end, the governing equations are deterministic, right? You look at them, there's nothing random about they're deterministic equations. They're not undeterministic. The issue is in their nonlinearity. There are a dynamical system, and any slight change in initial or boundary conditions is the problem. Really, the problem is us being unable to describe nature or an experiment to infinite precision, per se. Okay, and some say that's an inherent feature of nature. We cannot describe it really, and or we don't have the mathematical tools to do that description. Anyway, that's philosophy. So it's therefore somewhat foolish to say that we want to compute turbulence exactly. What we can do is think in terms of averages. We're going to get average properties of turbulence. That's the best we can, because the question of saying, I want to get the turbulent experiment, that's a silly question to ask. That question itself is a little bit dumb. No, that's not the right question to ask. What you want to ask is getting average properties, okay? I'm not going to go into, maybe next time we'll go into more details about scaling in turbulence, but what I want to get to, I'm still trying to give you a feel of turbulence and what it does, and to get to some working equations that we can use in practice to solve for turbulent flows, okay? But one of the key features in turbulence is what's called the energy cascade, and it was developed by Richardson in 1922. He was looking at some numerical weather prediction as well, and he was trying to deal with turbulence, and his hypothesis is, it says that turbulence consists of eddies, and we know what an eddy is. It's just like a vortex, it's a region of the flow that is rotating. And as we saw from the simulations earlier, you have eddies that are the size of the domain, eddies that are half of that, and half of that, and half of that, and half of that, and half of that, all the way down to the molecular scale, okay? And big eddies can contain small eddies, and smaller eddies can contain smaller eddies, and so on. And his idea was that large eddies actually break up, and they turn into smaller eddies, and those eddies also break up and turn into smaller eddies, and they keep breaking up all the way until we get to the molecular scale, and that's called the energy cascade mechanism. Okay, and some nomenclature. An eddy is considered to be a turbulent motion of size L, this script L, and these eddies range in size from the flow length scale to the smallest eddies in the flow. Kolmogorov then showed that the smallest eddies are actually all the way down to the molecular scale. Each eddy has a characteristic length and a velocity, and you can define a time scale for the eddy L over U. And obviously, the length scales, these length scales change. So in one flow, one snapshot of the flow, you're going to see velocity and length scales going all the way, from the smallest Reynolds number to the largest Reynolds number. And each eddy has its own Reynolds number, right? So there's the large eddies that are very, very big in size and large velocity. They have a very large Reynolds number, all the way to the smallest eddies that have a Reynolds number of 1, where viscosity and inertia are equivalent, and that's kind of the smallest eddy you can get to. Okay, so schematically, this is what happens. You have large eddies; they break up into smaller eddies, and yet into smaller eddies. For large eddies, Reynolds number is large; therefore, viscous effects are negligible, and that's what we call the energy-containing range. So these are the eddies that keep the flow going. Okay, that feed the flow, because there's dissipation is negligible. The only way for these eddies to be sustainable is for them to release their energy into smaller eddies. And then you reach a point, as the eddies keep shrinking in size, the Reynolds number is changing. They reach a point where viscosity becomes important, and they dissipate the energy. Okay. So in a way, one way to think of turbulence, again, like I alluded to last time, is nature doesn't allow for instability to happen, for perturbations to grow indefinitely. Okay, there should be something that will stop these perturbations. An explosion, for example, is something that stops an instability. In turbulent flow, obviously, imagine you can, turn on your faucet and increase the Reynolds number. Your faucet, thankfully, doesn't blow up in your face, right? But anyway, for nature to sustain the growth of perturbations, it introduces the energy cascade mechanism. It says, I cannot deal with this. I'm going to start ripping these eddies apart. Okay. And the idea is that large eddies are unstable and break up, transferring energy to smaller eddies. The smaller eddies undergo the same process, and so on. And this energy cascade continues until the Reynolds number is sufficiently small that energy is just dissipated by viscous effects, that the eddy motion is stable, molecular viscosity is responsible for dissipation. Really, it all goes into heat. And Richardson described this with a beautiful poem. It says, big worlds have little worlds which feed on their velocity. So the little worlds feed on the velocity of the bigger worlds. And little worlds have lesser worlds, and so on to viscosity. Okay? Big worlds have little worlds, which feed on their velocity. And little worlds have lesser worlds, which feed on all down to viscosity. Anyway, and one thing, yes?
So if I were to recite that during the qualifying exam, would I get extra points?
I would give you extra points, but I don't know about the other professors. So you could tell them, as you understand, turbulent. Grab a chair, put your leg on the chair. Okay. It turns out that also turbulence has somewhat of a, at least isotropic turbulence has somewhat of a universal energy signature. So if we take a snapshot of the simulation we looked at before, just take a snapshot, and somehow calculate the energy contained in eddies of the same size and add them up. So let's say you have eddies of size L0, like you have 4 eddies, 4 of those eddies. You add the energy contained in those 4 eddies. And the energy is U squared, 1 over 2 U squared, that's kinetic energy. And then you take eddies of size L0 over 2, and there's like 15 of those. You add up all the energy of those, and then so on and so forth, all the way to the smallest scale. Okay? And then you plot the energy contained in the eddy versus the eddy size. Okay? And what I'm plotting here is the energy versus 1 over the eddy size, which is the frequency. Okay? Which is the frequency in this case. So think about this as a Fourier transform. You're looking at the frequency. It turns out that turbulence has a distinct energy spectrum that looks like this almost always. Okay? There is so over here we have the largest scales over here, although we start from 0, but that's 1 over the length scale. So this is the largest length scale all the way to the smallest scale. And the large scales, okay, think of this as like several times the size of your domain. And then you see over here, at this point, you have the largest energy. These are the eddies that contain the largest energies in your domain. They're on the order of the size of your domain over 2 or over 6. Those are the largest eddies that are contained in the flow. There's a lot of scaling for this in Kolmogorov's hypothesis. We can talk about this on Wednesday, hopefully. But then there's a point beyond which energy is just continuously decays linearly on the log-log scale, and then is dissipated suddenly over here at these small scales. And that's a key signature of turbulence. Okay, so this explains the spectra we were talking about with the turbulence generator the other day. So anyway, that's a unique signature of turbulence. So I'll give you an example of how this is useful. In simulation, sometimes you want to introduce some randomness. Okay, in an inflow boundary condition, for example, you want to introduce some randomness. You want the inflow to fluctuate. Okay, just to trigger turbulence per se. And one would go and put in a random number generator. Okay, just you have a parabolic velocity profile, add a random number generator at each point of the inlet. You know what? It's not going to do anything. That randomness will dissipate in a single calculation, single time step calculation. Why? Because the random number generator does not have this energy signature. Okay? So you cannot, so turbulence randomness is not random in the sense you just like pick it's like a Brownian, or random walk, or just pick a random number. Okay? No, it is governed. The reason you get this energy signature is because of the Navier-Stokes. Because this turbulence is governed by the Navier-Stokes. Okay? Okay. So now we can start talking, now that we have a sense of what turbulence is. It's chaotic, it has mixing, it has a lot of vorticity. We cannot describe it, unless we know the initial conditions very well, etc. But why can't we just compute it? So we have the Navier-Stokes, okay? And we should be able to just compute it. Well, before we jump there, let's dig a little bit deeper. Okay. So there are 3 tiers in our attack of simulating turbulence. Direct numerical simulation, which I just said. We know the Navier-Stokes equations. We just compute them and change the initial condition slightly, or perturb the initial condition, do another calculation, and run that experiment 1,000 times. And it's a good random sample. And then average all the results to get average properties of the flow. Okay? That's called DNS, direct numerical simulation. We just take the Navier-Stokes, we simulate them directly. Then there's large eddy simulation that says, we're going to fully resolve some of the scales and then model everything else. Why do we do this? Wait, hold on for a second, because this is going to turn out to be very, very, very expensive. Multiple, very to the power 9 over 4th, actually expensive. And very being very large number. Very, very large number. Very to the power 9 over 4. Okay? Large eddy simulation says, no, we're going to capture the energy containing eddies, these big eddies, And we're going to model everything else. And then there's the Reynolds average Navier-Stokes equations, RANS. You've heard of RANS, right? You've heard of RANS modeling, Reynolds average Navier-Stokes equations, where we're going to model everything. We're not going to capture anything in the turbulence. We're just going to assume we're going to compute average properties, okay? So in terms of the spectrum, remember the spectrum describes the energy contained in the scales of turbulence. We have the large scales at the left, the smaller scales on the right, and the energy contained. With RANS, we're going to model the entire spectrum. We're going to model all the energy, or everything, all the scales. We're not going to compute those scales. We're going to model them. Okay, we'll see what that means in a second. But with LES, we're going to compute some, right? Say we want to compute up to this eddy size, okay? And we're going to model everything below that, the small scales. And in DNS, we're going to compute everything. Okay, all the way from the large scales to the small scales. Okay, the problem is that with direct numerical simulation, again, the goal is to compute all the scales from the largest domain size scale to the smallest viscous scale. But this means that grid points have to be smaller than the smallest scale to be able to capture it. Let me give you an example. Can I use my new model? Okay. Let me give you an example of what this means. Okay, so let's say you're trying to plot this curve, okay, numerically. And you only have 2 points to compute. What you're going to capture is this point and that curve is going to look like a straight line, right? So in order to capture the variation in this curve, well, you need more points. You need a point here, you need a point there, point there, point there, point there, point there. In other words, your spacing of points, your resolution, needs to be fine enough to capture this variation over here. Okay? Does this make sense? Okay, so what if then I also, you do something like this. Do something like this. Obviously, in order to capture this, you need a lot of points over here, numerically, or even you're plotting it. Let's say you're plotting this curve. You just do points. You're not gonna plot anything. You're just gonna pick this point and maybe that point, and then you're gonna get is this, which is wrong. Okay, so you need a lot of points to capture fine details. And the same thing when we're doing fluid flow. So typically in fluid flow we have in calculation we have what we call these cells, where each cell contains one value for the velocity, okay? And let's say you have an eddy. Okay, if you have an eddy that's this big, well, you can capture it because you have velocity here, velocity there, velocity here, and velocity here. You can have an idea of what the eddy looks like. But what if your eddy is this small? Well, obviously you cannot capture that eddy because you only have one value of the velocity there, which is constant. So therefore, in order to capture this eddy, you need to have grid points that are smaller than the eddy size, maybe 1/8 smaller, okay? And that's a problem, okay? We'll see why. Because the size of the eddy is so small that makes the number of grid points really infinite. Okay, we'll relate that to the Reynolds number in a second. But also you have time scales. Remember, you have spatial scales, these little eddies that are rotating, but you also have the rate at which these eddies are rotating. You have the large eddies moving at a very slow time scale, but then you have the small eddies that are spinning really fast. And numerically, to capture those very, very small eddies, the time scales, you have to move at a time rate smaller than they are rotating in order to capture the rotation, right? It's like, if you're videotaping them, You want to have a frame rate that is faster than the rate at which they are rotating, right? And that makes the simulation, DNS, the simulation of turbulent flows, really, really expensive, okay? And only doable for small Reynolds numbers. So let me give you an example. This is a practical calculation that gives us an idea of what the size of the smallest eddy is, okay? It's related to the Reynolds number. And you can estimate that the number of grid points in each direction, okay, scales with the Reynolds to the power 3/4. So in 3 dimensions, that's n cubed, that's Reynolds to the 9/4. That's very to the power 9/4, okay? Where very is a very large number, okay? Now, we can get an idea of how much this would cost us based on, this is an old calculation from Stephen Pope's book, a computer that does 1 gigaflops, so flop is floating point operation per second, okay? So for a Reynolds number of 94, we need about 10 to the 6 grid points, and however many million time steps, 10 to the 3, million time steps. This would take about 20 minutes to calculate. But Reynolds 24 is really not that turbulent, okay? So Reynolds is a very small Reynolds number. So the flow is probably laminar. That's why you can do this calculation really easy. This is just a channel flow, or a channel with a backward facing side. Now notice as you increase the Reynolds number to 1500, which is a reasonable Reynolds number, you need 13 days to do this calculation. 6,000, you need 20 months. 24,000, that's just like a standard Reynolds number. You need 90 years. Okay, so you start the simulation when you're born. Let's say you survive until 90, and you're like, the simulation is done. Now we can visualize the result. And if you want to do 96,000, you need 5,000 years.
That's if you only have one CPU, though, right?
Even if you have hundreds of thousands of CPUs, you're not able to push that much higher. Yeah, that's a good point. But that's 1 gigaflops. We can say, the way you can do this calculation is not worry about the number of CPUs. Take the total speed of a supercomputer, like 1 teraflop, for example. You'll only move the Reynolds number maybe 1 order of magnitude, 960,000, and then what? That's hardly practical, okay? Because in practice, our Reynolds numbers are like 10 to the 7th, okay? And so that will make it's still very expensive. It is very expensive. You're churning on these machines, and you get one realization, just one realization. Okay, and that is hardly any statistical evidence, one realization. The way you do it, you want to repeat the simulation and change the inlet conditions, perturb the inlet conditions a little bit, and then get another solution, another solution, another solution, and then you get statistical properties to understand what turbulence is doing. Otherwise, with one realization, you cannot understand turbulence, okay? So that's a problem, okay? We cannot do DNS except for very small Reynolds numbers. There are people who do it, certain cases, certain types of problems, but it still take a few months, and that's very expensive. Okay, and there are also issues with parallelizability of these, so that's a different world in computing. Okay, all right. So we're not going to talk about LES. We're going to just jump directly into Reynolds averaging, and we don't have to call it Reynolds averaging. We just call it averaging. And the idea here is rather than taking the instantaneous velocity profile, what we are generally interested in as engineers, even scientists, is an average sense of what the flow looks like. Okay, just an average property of what the flow looks like. So Reynolds said, okay, let's decompose the total velocity field or any property in the flow, because it's not only the velocity that's fluctuating, it's also the pressure. And if the density is changing, it's also the density is fluctuating. If the temperature is changing, if you have heat transfer, also the temperature is changing, right? Because the temperature is transported by velocity, density is transported by velocity, and if the velocity is fluctuating, then everything else is going to be fluctuating. So then Reynolds said, any property phi, we're going to decompose it into some average. We'll define what the average means, but think of this as a time average now, plus a fluctuating component. Okay? And he said, let's just be interested in calculating the average. Okay? Now let's look at some properties of averaging. We're gonna call the average We're going to denote it by phi bar or these brackets, phi. And averaging is a linear procedure, okay? And so it has the following properties. We'll show that the average, or we want to define an average in a way that the average of the fluctuation is 0. Okay, so let's go back to the first equation. We said any property phi, instantaneous property, that is turbulent, is equal to an average value plus a fluctuating value, phi prime. Average value, phi bar, plus a fluctuating value, phi prime. We want to define the average in a way such that if we take the average of this equation, we get this guy, right? So therefore, the average of phi prime needs to be 0, okay? A time average, for example, satisfies this property, okay? And the average of the sum is the sum of the averages, because it's a linear process. The average of a constant times phi is equal to the constant times average phi. The average commutes with the spatial operators, div and grad. So average of grad phi is grad phi average, okay? And the average of a product of two turbulent quantities that is not equal to the product of the averages of the turbulent quantities, because that's a nonlinear term. Instead, A is A average plus A prime, and B is B average plus B prime. And then you do the multiplication, you get AB plus AB prime plus A prime B plus A prime B prime. And then the average commutes with the addition. And what you get is AB, average AB plus average of average A plus B prime times B prime plus A prime B, average plus A prime B prime, and that's equal to AB plus A prime prime B prime. Why did this term disappear? Fluctuation, yeah, because the average of A times B prime is equal to A times the average B prime, because that's just an average. It's like a constant value, right? Think of it as a constant value. And then the average of B prime is 0, as we define it, okay? Okay, and we'll just talk about the types of averages before I let you go. There are numerous types of averages. I like this last one, but let's talk about them. For the classical definition of the average is that it's a time average, okay? So you just take an average over a long time, but that time, needs to be small enough to capture, some features of the flow, okay? But that sometimes doesn't work if you have a time-dependent flow. So you have to pick your time average very carefully, okay? Another one is to use this is spatial average. So this is time average as talked about. The other one is a spatial average, where you just average over a region in space or over the entire domain. The most useful average is the ensemble average. So say your average is an average over experiments, okay? So we don't have to run those experiments. We just define the average that way and interpret it that way. The beauty of this definition is that it allows for time dependence to still be involved. You're not averaging over time, okay? You're averaging over experiments. And therefore, you can retain basic features of the time-dependent flow, okay? Average features of the time-dependent flow. Next, what we're going to do, we're going to take this decomposition and put it in the Navier-Stokes equations. That's all there is to looking at average turbulent flows, okay? We'll do that on Wednesday. And that'll be it, okay? Any questions? Did you learn something new today about turbulence? Okay, good. We'll learn a little bit more next time. Thank you very much.